In this video, we're going to look at what stability means in the Compose Compiler plugin and how it infers it by looking at a type. Stability is really helpful because it allows us to skip the execution of a composable body. Let's look at an example of stability. So here I have a composable method user screen, which will create a column and a row in that column for each user. It's going to use this user model to extract information. This user model is unstable, and we'll look into why. So you have a mutable name, I have a friends, which is a list, and I'm also using external type. When you do a performance analysis of recompositions with unstable types, you'll see that the recomposition count will keep increasing, maybe when some action happens on the screen. So what makes a type stable? One is immutability. You always want to strive for immutability. In our case, the name is mutable. That's a problem. Another things that are problems is the list I'm using right here. I'm also using a unstable local date time. What are the implications of using unstable types? In the Compose Compiler plugin, you'll see a dedicated transformer it's just for being able to look at your IR types, and it maps it to a stability. Stability is defined in the Compose Compiler plugin using a seal type, a seal class, as we'll look at. So here in this example, we had all these problems in red. What does that mean when you look at the transformed IR code? In the transformed IR code, what you'll see is that this bit masking logic gets affected because when the transformer is going through all of your slots, it's looking at each type in each slot, and it's going to look at whether it's stable or not, and based on that, it's going to set stability bits, unstable or stable. And that has an effect on the skippability of a composable function. It also has an effect on how the composer is doing equality checks. So in this case, is using an instance equality check. But if you had a stable type like this model, if you're using it in this example composable function, and you look at the IR code, it looks like this. The IR code in this example is using the changed method, so it's doing an equality check. So how do you analyze the Compose compiler plugin stability checking? How do you get a report of all the stable and unstable types? So what you'll see in the Compose compiler plugin is that there are a set of transformers. And these transformers, they all get provided through their constructor with a module metrics. There's a concrete implementation of a module metrics. It's an interface, and it has different methods to record information, such as the number of composable functions you're using, the number of lambdas you have, the number of classes you have, and has information about skippability, whether it's restartable. So it's very useful information, and this is what a compiler report looks like, all these different statistics, and you can get them by turning on this configuration right here in the Compose compiler. And what you could do, something that's useful, is to create a CI build process. This is useful for release builds, by the way, where you could take a release build and you could set the Compose compiler configuration for generating a report, and you could store the stats and do a comparison analysis on them on the before and after. So this is what a report looks like, and it's going to tell you in red which functions are not restartable and which functions are unstable. So how is stability determined underneath the hood? So as I said before, stability is determined underneath the hood by looking at, by mapping to a seal class. There's a seal class which is used in the Compose compiler plugin to model stability. And the plugin goes through each IR type and it determines like which type of stability it is. So in this example, when the class stability transformer is going to get this type, there's a visitor method which is called visit IR class, and in there it's going to utilize something called the Stability Inferencer that we'll look at. Ultimately, what this transformer does is that it synthesizes this annotation on a particular type. And the parameters, the argument of this annotation tells you like how many parameters it was able to infer stability for. In this case, 0, because they're all unstable. So the stability inferencer is provided through the constructor to the transformer. So stability is modeled as a seal class, and you have different types of stability. You have certain parameter, you have combined stability. Sometimes stability cannot be determined during compile time. It can only be determined like during runtime. So what does an unstable stability look like? What does it map to? Well, it uses a stability.certain class, and it passes a Boolean of false. That's unstable. For this external type, is going to do a runtime. So you could get a report of this information from the compose compiler like this. So what are the rules for stability? First rule that it has to check is it has to check whether you're using are you using types that are known to be stable. So it has something called known stable constructs, and what it's able to do is that it's able to check whether you're using a primitive type, are you using a result or a pair or triple, and if you are, then it's going to mark it as stable. So certain things are unstable, like for example this generic right here, this will get mapped to a stability.certain with a false. This is makes it unstable. But if you're using like, if you may have like Dagger lazy generated code in your parameters, and for that it will mark it as stable. Or Guava collections or Kotlin immutable collections. So what if you're using Pertos? Or Pertos, it's also able to mark it as stable, and this was added recently in this PR in the ASOP. Not recently, but a couple of months or years ago. And there's an extension on IR class type in the compose compiler. It basically is able to check whether the parent class is a generated protobuf, and that's really useful for if you're using like prototypes, for example, in your composable function. So what about interfaces? So the compose compiler plugin, what it does is that in this method, what it's able to do is going to mark it to an unknown stability for interfaces. So what about if you have a hierarchy like this, where you have class A and B, it's a pair, it's going to mark it as runtime stability for that. One performance tip I have is if you're using external types is to use these annotations, and the compose compiler plugin goes in and looks for these annotations when it's determining stable or unstable. So for example, over here in this case, one way I could handle this is by using the @stable annotation on this type. So I'm basically able to go in and the compose compiler plugin, you'll see it checks whether these markers are being used to mark it as stable. So internally, that's what it's doing. There are two stability markers, @stable and @mutable, and you're able to mark it. You're able to mark your type with them. When you resolve the stability issues of your type, it will synthesize an annotation where parameters, in this case, is 3 because there are 3 stable parameters for it. So that's what that the argument means in that annotation there. So when you mark everything, it makes the compose function restartable, stable type. It also makes it skippable, and that's really important to know. Something else which I didn't share much about here is that by default now there's a feature flag which is set on called strong skipping that is on by default now. And you could test it out. You could also opt out of that by setting a configuration file, things you want to opt out of the strong skipping. If you want to learn more about that, check out my talk from KotlinConf on compose performance. In the next video, we're going to look at how the compose compiler plugin is able to do tests internally.